Welcome to the lecture on addition and elimination reactions. This is Unit 3, Part 2. Under Part 2, I am going to discuss hydration and hydroxylation in carbon-carbon multiple bonds. This is the detailed syllabus of Unit 3. Chapter 1 is on addition to carbon-carbon multiple bonds. Chapter 2 is on elimination reactions. Hydration of an alkene can be carried out by different methods. One among the several methods is acid catalyzed hydration. An alkene can be hydrated with an acid catalyst. For hydration of alkene we need water, an acid as a catalyst. So water takes up a proton from acid, generating hydronium ion. This hydronium ion is the source of H plus ion. So from hydronium ion, the alkene, here I have given an unsymmetrical alkene, which means both the ends of the double bond are different. So this unsymmetrical alkene takes up a proton from hydronium ion, for which this pi bond breaks to give a plus on more substituted carbon, minus on the less substituted carbon. So the minus takes up a proton, expelling a water molecule. So once H plus is added here, the other carbon, double bonded carbon, gets a positive charge. So that way a carbocation is generated. So carbocation is an electrophile. The water expelled from here is a nucleophile. Therefore, in the second step, the nucleophile reacts with the carbocation. So water has an oxygen which has two lone pairs. So one of the lone pairs reacts with the carbocation, making a new bond. Once it makes a new bond, oxygen will get a positive charge, and in order to neutralize that, a H plus ion is removed, and finally we get OH. So we started with an unsymmetrical alkene. One side is more substituted, the other one is less substituted. To the less substituted carbon, H plus is added. Therefore, a more substituted, more stable carbocation is generated. And with the carbocation, water reacts here, adding a OH. So hydrogen is added to less substituted carbon. OH is added to more substituted carbon, and this kind of product is called Markovnikov product. Here I have given an example for hydration of an alkene. This is an unsymmetrical alkene with which we are adding a source of electrophile, hydronium ion. So the H plus will join with the less substituted carbon, because as the electrophile approaches this double bond, the pi bond breaks to give minus on less substituted, plus on more substituted carbon. So the minus on the less substituted carbon takes a proton from the hydronium ion. So minus joins with H plus. So this carbon will have positive charge, and that will be attacked by the nucleophile water, and that results in the formation of tertiary butyl alcohol, and in this reaction we are getting 71% of this tertiary butyl alcohol, which is a Markovnikov product. The problem with this hydration of alkene by water with acid involves a problem, that is, the carbocation intermediate generated in the reaction sometimes undergoes rearrangement. The primary carbocation becomes secondary or tertiary. So likewise, the carbocation intermediate generated in this reaction undergoes rearrangement if it is possible. I have given an example for that. So here I have given an unsymmetrical alkene and I have added dilute acid. So hydronium ion gives H plus. That H plus approaches the pi bond. The pi bond heterolyzes to give a minus on the less substituted, plus on the more substituted carbon. So H plus is added to the terminal carbon. H plus is added here because this carbon had a minus, and the next carbon is holding the positive charge. It is a carbocation, secondary carbocation. Now this carbocation can undergo rearrangement to become a still more stable tertiary carbocation. How it happens? So the carbon next to the carbocation is labeled as carbon number 1. Carbocation is labeled as number 2. From carbon number 1, an alkyl group comes out as alkyl anion. So CH3 here comes out as methyl anion and joins here. So if this methyl is shifted to this carbon, you will have a positive charge here, that is a secondary tertiary carbocation. So in this rearrangement, a secondary carbocation is converted to tertiary carbocation, which is more stable. And now the water molecule, the nucleophile, attacks at this carbocation, making a new bond. After deprotonation, it gives an alcohol. So this is the problem with acid catalyzed hydration. There is a possibility for the rearrangement of carbocation. Here is an example for hydration of an unsymmetrical alkene using mercuric ion catalyst. With an unsymmetrical alkene, water, an acid with mercuric salt are added. Alkene, of course, is dissolved in an ether-like solvent. With that, all these are added. And here, the reaction leads to formation of Markovnikov's product. Hydrogen of water is added to the less substituted carbon, and the OH is added to more substituted carbon. Therefore, this is Markovnikov's product, but the advantage here is we are getting a product which does not involve rearrangement of carbocation. And this type of hydration with the oxymercuration involves two steps. Here I have given an example with mechanism. This is an unsymmetrical alkene, propene. With that, we add mercuric acetate. So the pi bond breaks to give a negative charge to the less substituted carbon, positive charge to the more substituted carbon. The negative charge attacks mercury, substitutes acetate. It replaces the carbon ion, replaces this acetate, substitutes this acetate, and then simultaneously a pair of electron present in mercury is making a bond with the carbocation. So this is taking place, both the steps are taking place simultaneously, resulting in the formation of cyclic mercurinium ion. There is no separate carbocation generated. Both the double bonded carbon atoms are now bonded with mercury in cyclic mercurinium ion. And now water attacks the more substituted carbon as nucleophile, because the more substituted carbon is expected to have higher positive charge than the less substituted carbon. So this is a more positive center. Therefore, it is attacked by the lone pair of water, and the bond with mercury is taken back to neutralize mercury. Now, after the attack of the water molecule here, oxygen has got positive charge. There is an oxonium ion. It undergoes a deprotonation to give OH. So in the first step, with the more substituted carbon, OH is added, and the second carbon is having the mercuric ion. In the second step of the reaction, the hydride from sodium borohydride attacks the less substituted carbon, replacing the mercury. So during this reaction, sodium borohydride reduces the mercury to metallic mercury, and hydride ion is added to the less substituted carbon. So this is the final product of the reaction. These two carbons were having a double bond here in the beginning. So this is the less substituted carbon to which hydrogen is added. With the more substituted carbon, OH is added. So this is again a Markovnikov product, and this kind of oxymercuration followed by reduction does not involve carbocation rearrangement. Both acid catalyzed hydration reactions as well as oxymercuration reactions take place with the alkyne substrates also. The addition follows Markovnikov's rule. The hydration of alkynes also follow Markovnikov's rule. The acid catalyzed hydration reaction is little slow, but it speeds up. The reaction is speeded up when mercuric salts are added as catalysts. The initial product of the hydration reaction with alkynes is enol. When hydration takes place with an alkyne, the initial product is an enol, and that enol tautomerizes to give a stable molecule, an aldehyde or ketone. So here I have given an example of hydration of 1-pentyne with water and acid along with mercuric salt as catalyst. So in this reaction, H plus is added first to the less substituted carbon here, generating a carbocation here, and that joins with the mercuric ion. So cyclic mercurinium ion will be formed, that will be attacked by water, and that results in enol. So now you can see with the less substituted carbon, hydrogen has been added. With the more substituted carbon, has been added, and the product is enol. Enols are unstable, so the enol tautomerizes to a stable ketone or any carbonyl compound like aldehyde. In this reaction, it is ketone. Here is another example for hydration by oxymercuration followed by reduction. So here the same mechanism is followed. Formation of cyclic mercurinium ion followed by reduction. And this process adds a hydrogen to the less substituted carbon. So the CH becomes CH2 here, and then OH group is added to the more substituted carbon, and this is again an enol, and this enol undergoes tautomerism to form a ketone. So the advantages of oxymercuration reduction reactions are there is no rearrangement of carbocation taking place here, and the reaction is faster with mercury catalyst. The next reaction we are going to discuss now is dihydroxylation of carbon-carbon multiple bonds. A dihydroxylation reaction adds two OH groups to a double bond to form a diol. The reaction of an alkene with a cold alkaline potassium permanganate or with osmium tetroxide in an aqueous hydrogen peroxide solution readily yields a 1,2-dihydroxy alkane. These 1,2-dihydroxy alkanes are called as glycols. So with KMNO4 as well as osmium tetroxide, the dihydroxylation reaction yields syn-diol or cis-diol. Here is an example for dihydroxylation of an alkene with aqueous solution of aqueous alkaline solution of KMNO4. So here KMNO4, potassium permanganate, reacts with an alkene. From the double bond of manganese oxygen, one bond breaks, goes to oxygen, and it attacks the alkene. So when this oxygen attacks this alkene from here, the pi bond breaks and goes with a negative charge to the adjacent carbon. That negative charge attacks oxygen. When a new bond is made here, this pi bond is shifted to manganese, so that the 7 plus oxidation state of manganese is reduced to 5 plus here, and this is a cyclic manganate ester. This cyclic manganate ester contains the two oxygen atoms on the same side of the two carbon atoms which were having the double bond earlier. Now with this cyclic manganate ester, the alkaline solution, the hydroxide, attacks manganese. We can see there are 5 bonds with oxygen, the electronegative atom oxygen. So through all the 5 bonds, oxygen atoms are pulling the electrons towards them. Therefore the manganese is an electron deficient center, and it is readily attacked by an anion hydroxide. So when a new bond is made here, this manganese oxygen bond breaks to generate O minus, and it takes up a proton from a water molecule and becomes OH here. And the same process is again repeated. One more hydroxide attacks the manganese, making a new bond, and this bond is shifted to oxygen to give a minus. That minus takes up a proton from water. That way, two OH groups are introduced to the double bonded carbon atoms, and both are on the same side. This is because the reaction intermediate is cyclic manganate ester, which is having the two oxygen atoms on the same side of the double bonded carbon atoms. As we have seen with alkaline K-monophore, osmium tetroxide also reacts with alkene, forming a cyclic osmate ester, and it reacts with the aqueous solution of hydrogen peroxide to form the cis diol, as in the case of potassium alkaline K-monophore. The osmium tetroxide catalyst is being regenerated completely in this reaction. So far, we had been discussing the generation of syn diol with alkaline K-monophore or osmium tetroxide, and how to make trans diol, how to add two OH groups from the opposite sides of the carbon-carbon double bond. Epoxidation of alkenes followed by treatment with dilute acid generates trans diol. So epoxidation is done with per acids. How that reaction is taking place? So here we can use a per acid. Here I have given trifluoroperoxytic acid. So here we have C double bond O carbonyl OOH. So CO3H, that is per acid. And in the other side we have an electron withdrawing group. So if the per acid contains electron withdrawing groups, it is more reactive with alkene. So the other per acids we are using very often is metachloroperbenzoic acid and other benzoic acid, perbenzoic acids with the electron withdrawing groups. So here we can see this oxygen of the per acid with its lone pair attacks the double bonded carbon, and this pi bond is shifted to this carbon, and that is again attacking this oxygen. And this process, as I have shown with the arrow marks, results in the epoxide, the oxyrane. Once this oxygen is connected, you can see this bond comes out here and it is moving. This bond is shifted to oxygen, making O minus, and it takes up the proton from here, resulting in trifluoroacetic acid. And this oxyrane, the epoxide, reacts with the dilute acid. So the dilute acid is nothing but hydronium ion. With water, the acid reacts, generating hydronium ion. And that hydronium ion protonates the oxygen of epoxide. And after the proton is given here, what is remaining is water. So water with its lone pair attacks from the backside of the ring. It attacks from the backside of the ring, making a new bond here. And this bond is shifted to oxygen. And this is how a trans diol is generated. So if at all you want to generate Cisdiol or syndiol go for alkaline KMNO4 and osmium tetroxide with peroxide. If you want to generate transdiol from alkene, generate epoxide and treat it with dilute acid and you will end up with transdiol. Thank you.